Hi guys, welcome back to my channel. Today we're going to an educational video. This time it's about math, specifically linear algebra, and this is topic 5.3 from David Lay's linear algebra textbook. And this section is all about diagonalization. In a previous section, I believe in chapter 2, we talked about an LU factorization. That's another type of matrix factorization that diagonalization also is. And this time with diagonalization, you're going to have this type of factorization where you have a matrix A, and this, let's say this matrix is diagonalizable. So this, it could be saying it's we can say the invertible matrix P times D times P minus 1. So that's P inverse. So P is invertible, and uh, D is of course a diagonal matrix, and these are conditions for diagonalization factorization. So, what are the practical uses of a diagonal matrix or diagonalization factorization? So, let's say you want to find a power of a matrix. So, this is a pretty tedious process, right? You're going to need to say you're doing a to its cube, right? Then you're gonna have to have these components A, B, C, D in each matrix, and you have to do that 3 times over. Just imagine how tedious this gets. You're gonna have to do this A plus AC, and then uh, A plus BC, A. Then you're gonna do this again with AB plus BD. Then you imagine you have all this complicated stuff with 2 different terms. And have to do that again with a third term. That's gonna be very difficult, right? That's very time consuming. Well, you introduce the diagonalization where you can express a cubed instead as PD p minus 1 or p inverse. And then again, 2 more times. And notice what we're going to do when we multiply p and p inverse together. You can see this goes pretty nicely. You'll get PD p inverse p d p inverse p d p inverse. And these both cancel out to the identity matrix. And this will just be p d cubed p inverse. And it can be shown that similarly a to the nth power is going to be very similar, where you can get p d to the n and p to the 1. And since d is the diagonal matrix, all you need to get for d to the nth power will be raising each of its components, non-zero components, which are on the main diagonal to the nth power. So let's see that being applied in the practice problem real quick. So here we're being asked to find a to the fourth, where we're given p and d in the diagonalization matrix. So let's see what we can do with it. First thing we're going to need is finding p inverse. And since this is a 2 by 2 matrix, we can use the 2 by 2 matrix formula. And then we can label this. This is A, B, C, and D. We have 1 over AD minus BC to determine it. And then the components, you flip A and D, D and A, and then negate B and C. This formula will end up saving a lot of time for us. So this will be 1 over 10 minus 9. So that means we're not going to need to apply a multiplier since this is 1. And then we're flipping 2 and 5, so we get 5 and 2 here. And then we make the negatives positive for the 3's. Now we're ready to do the diagonalization. So d to the fourth is we have zeros here. 1 to the fourth is 1, and then negative 1 to the fourth is also 1. So we can put the identity matrix here. And now we can find a to the fourth with this formula from before. So we, instead of n, we use 4, so we just get p d to the fourth and p inverse. And now we just plug in formulas multiplying. We have this p. That the diagonal matrix is an identity 2 by 2 matrix. And then we have p inverse here. since we're multiplying by an identity matrix here, we can simplify this pretty quickly. And then it's just a standard matrix multiplication problem. So you can see that the diagonalization here saved us a lot of problems. And that could guard a lot against arithmetic errors you can make here. So here we have a standard matrix multiplication protocol. So we get 2 times 5, 10, minus 9. And then first row times second column, 6 minus 6. Second row times first column, so negative 15 plus 15. And then second row times second column, negative 9 plus 10. And the answer we get after simplifying this would be a 2 by 2 identity matrix. You can see that calculation is a lot simpler after you apply the diagonalization. This is going to be a safe introduction to our diagonalization theorem. This is the most important part of this lesson. The diagonalization theorem states that an n-by-n matrix is diagonalizable if and only if A is n linearly independent eigenvectors. Basically, you're going to have to... this theorem is going to establish how we're going to have our processes to diagonalize matrices. And the proof is involving concepts with eigenvalues, obviously because you have eigenvectors there. And it revolves around the equation for an eigenvalue where you have a n equals lambda n. And you can see when we use a equals p times d times p inverse, you can multiply both sides by to the right by p, and you get a times p equals p times d. And if you write out the matrix multiplication form for each column, you can see there is an eigenvalue relationship here. So it will look like A, and then you have column 1, column 2, so on for P, and then you have the lambda values instead for each of the, and so on. And that shows the eigenvalue relationship. And we know that P is invertible, so that's why we get the linearly independent part, because a invertible matrix must have linearly independent columns. Let's see how to diagonalize matrices ourselves using that information. But first, let's learn how to interpret diagonalization theorem by looking at an example. So here we have A, of course, P, D, and P inverse. So in the terms of the diagonalization theorem, in D, we're going to see our eigenvalues. So we can see there's a repeated eigenvalue here for multiplicity 2. So our eigenvalues would be 5 and 1. And let's say this again because there's multiplicity 2. We can write out like that. And here are our bases for our eigenspaces. And the important thing to note is the columns in D correspond to P. So your diagonal matrix can have the eigenvalues in any order as long as each of the basis vectors for the eigenspaces correspond to the right eigenvalue. So you can see that to solve this problem, we have eigenspace for 5 would be just the first vector here, so 1, 1, 1. And then eigenspace for 1, we have 2 vectors here. And that would be these last 2 vectors that we can find from this factorization. And this is an important interpretation that we'll use when we're diagonalizing. And basically, you're reverse engineering this process that we've been giving here. And that'll let you find your eigenvectors. And when you're diagonalizing, you're basically using the bases for the eigenspaces to create the matrix instead of using the matrix to get those for you. So it's the reverse process. Let's tackle a diagonalization problem together to see how to do this. We're given the eigenvalues here, so our first step would be finding what the resulting matrix would be, because to find the eigenspaces, we need the null spaces of the resulting matrix when we do A minus lambda I. So let's do that for lambda equals 1 first. So we have A minus I. And this would be subtracting from the diagonals. We have 7 minus 1, so 6. And then these two terms are the same. Then 2, then 5 minus 1, so we have 4. And then 8. Then negative 2, and then negative 5 minus 1. So we get negative 6 here. And all of these numbers are even, so we can take the first step of dividing everything by 2. So your overall operations like row 1 equals row 1 over 2, row 2 equals row 2 over 2, and row 3 equals row 3 over 2 if you're showing up row operations. We have 3, 2, 8, 1, 2, 4, and let's divide Tom through by negative 2 instead of 2 to make it easier for us. So we'll have 1, 1, and 3. And at this point, let's swap the first and third rows so that we can make calculations easier on ourselves. Okay. Now let's do row operations to make create zeros in our process to get to REF. So let's subtract row 1 from row 2 and 3 times row 1 from row 3. So you get row 1 would be the same, and we have zeros here. Then we have 2 minus 1, so 1, and 4 minus 3, 1. And then in the bottom we have 2 minus 3, so negative 1, and 8 minus 9, negative 1. When we add row 2 to row 3, row 3 will become a 0 row. Okay, now we are in REF. So our last step here will be to subtract row 2 from row 1 to make this REF. And then 3 minus 1, so 2. Okay, so we have two basic variables here, and this free variable is ultimately our basis vector. So we have eigenspace for E1 would be so x 1 equals negative 2x3, x2 equals negative x3, and then x3 is free. So yeah, that this is where we get our variable for x equals so x equals x3 negative 2 1 1 negative 1 1. So that's what our basis vector will be. And then now let's do the same thing for the eigenspace of 3. So that's a, so a minus 2i will be here. So we have 10 minus 3, 4, 4, 16, 2, 5 minus 2, so 5 minus 3, so 2, 8, negative 2, and then negative 5 minus 3, so negative 8. We can see easily that these three rows are multiples of each other. So we can, what we can do is we will subtract 2 times row 1 to row 2. We will subtract 1/2 times row 1 to row 2. And before that, we will add 1/2 times row 1 to row 3. This will create 2 0 rows. And to make things easier, we'll divide row 1 by 4. So we'll have it in REF. So to find the null space of this matrix, we have an REF already, so we can express this as one equation: x1 plus x2 plus 4x3 equals 0. And ultimately we will get x1 equals negative x2 minus 4x3, and x2 and x3 are free. And to simplify this to make it in parametric vector form, we will have x1, just x, the vector, equals x2, negative 1, 1, 0, plus x3, this will be negative 4, Wait, let me change this again. This is x3. -4, 0, 1. And we have a 2-vector basis for our eigenspace. So we have E3 equals -1, 1, 0, and -4, 0, 1. Okay, now let's create our P and D matrices. So here we can see our two eigenspaces here. So we have eigenspace for 1 and eigenspace for 3. Now let's create P and D. We know P are the basis vectors for the eigenspaces. So let's start with the 2 was for base the eigenspace of lambda equals 3, and the lambda equals 1, 1. And then we have D. And now we're going to make sure that we correspond each of them correctly. So we have these two representing 3, and the last one represents 1. So these are your lambda values. And this is your diagonalized form for the matrix. Another thing to note when you solve diagonalization problems like this is make sure you have enough before you construct P and D, make sure you have enough linearly independent eigenvectors that you get from the basis to the eigenspaces. You need the basis of eigenspaces to have enough eigenvectors to fill in the matrix to get a square matrix. If you don't have enough, then the matrix is not diagonalizable, and you can just say it's not diagonalizable and call it a day. That's the end of your problem. Sometimes it won't be possible to do this, which is inconvenient if you want to raise matrices to powers. But I guess you have to do what you can do. But if a matrix is diagonalizable, calculating powers will be a lot easier, both by hand and on computer. And that is the main practical application of using the diagonalization factorization. So hopefully after this video, you have both diagonalization and area factorization under your belt, and I guess make sure you know the diagonalization theorem well going forward, and thanks for watching.